Alrighty, so what we're going to do in this video there, statisticians, is we are going to take a nonlinear pattern, nonlinear form of our scatter plot, and we're going to transform it into a linear form. So one of the websites we use to gather our data is what we call Gapminder. And if you're interested, you can go to gapminder.org, and it's going to give us a lot of data. One of the scatter plot you can see below in figure 3.18 shows a scatter plot of data from this website. So what it's comparing is in 2015, it's showing the explanatory variable is the income per person of a country, and then the response variable is the life expectancy of that person at birth. So when we're looking at this right here, so what we're seeing is on our x-axis, we have the income per person living in each country. Each of these dots is a country. And then we've got the life expectancy of that person when they were born. So please notice, why are some of the dots different size? So always read what the scatter plot is showing us. So this scatter plot of the life expectancy of people in many nations against each nation's income per person. The color of each circle indicates the geographic region. So I know it's hard to see in black and white, but you can see these green ones are the Americas, the North Americas and South American continent. Yellow is European and Russian, European countries and Russia. Our reds are Asia and the Pacific, and then everybody in blue is Africa. Why are some of the dots different sizes? Because the size of each circle is based on the population of the country. Bigger circles indicate larger populations. So you can see that this is a nonlinear form. So go ahead. I would like you to take a minute, pause that video, and tell me, what conclusions did you draw? All right, welcome back. So what I saw, where is my, there we go. What I noticed from this is, as I stated earlier, this distribution is nonlinear. It shows that the income per person rises, the life expectancy rises quickly. So we go a little bit over on X, and life expectancy shoots way up. From an income per person of about 25,000 and higher, the life expectancy does not seem to increase as it levels off. So what I'm talking about is we rise very quickly until we get to about this X value, and then we just my graph just kind of levels off. All right, South Africa, Botswana, Equatorial Guinea appear to be outliers. Did you notice anything else? These ones, South Africa, Botswana, Equatorial Guinea, these are all significantly lower than the line I would use. It's not a line, my curve that I would use to describe that scatter plot. Did you notice anything else? Talk to me about it when we come back. What we can do with this nonlinear plot, though, because that nonlinear plot is great, but what we kind of notice is, like, everybody after this point, life expectancy doesn't really go up as money goes up. So what we can do is we can actually turn this more into a linear function right there. You can see that we can make it more linear. And we can do that by, instead of saying that we're going to look at the income per person, we're going to change what we're looking at. We're going to turn this into the log of income per person. So that's what we're going to talk about in this video, except we're not going to use logs. We are going to use powers. But I just wanted to point that out. We can change the form of my scatter plot by not looking at just the explanatory and response variable. We can change how we look at them. So we can transform with powers and roots. So if you go to a pizza parlor and you order a pizza, we normally order it by its diameter. So when you order a 10-inch pizza, that pizza has a 10-inch diameter, or you can get a 12-inch, a 14-inch, a 16-inch, however big across you want it. But what you eat is the area of that pizza. So to find the area of any circle, I would do pi times r squared. And if r is going to be some variable x, we can square it. And so that would give us x over 2 squared is going to be x squared over 4. And what we find is, what we create is a power model. Our power model, where we say, here is the value of a. The value of a is the number in front of x. And then p is the exponent that we are talking about for x. Boom, right there. And that's what we're going to be doing in this video. We're going to be using a power model. Now, a power model, P can be any power. It doesn't have to be squared. It can be cubed. It can be to the half power, to a negative power. Just understand P is a power. So when we're dealing with things, well, I'll give you a minute to pause this, but what I'm saying is we can take a nonlinear form and we can make it linear by using powers. So for instance, if we have distance equals a times time squared, you can see a equals a, p equals 2. We can, instead of doing length, I can do the square root of length. The time it takes a pendulum to complete one back and forth swing is the period. It's related to the length of the pendulum. So PA is going to be the number in front of the length, my x, and the P is going to be half. And if we divide by something that's raised to a power, remember that's always a negative exponent. So A is going to be A and P would be -2. Okay, so and I will tell you what type of model to use, so don't sweat the exponent so much. So here it is again. So if we transform the explanatory variable x to some power, we can still make a scatter plot, but that scatter plot is now going to be x to the power y. And I'm going to rewrite my linear model, my power model, as y equals a to the xp. So if I give you any non-linear relationship between x and y, I'm going to give you a curve form of some kind, create a linear model between xp and y. So that's going to let us take that curve and make it into a line like we saw with the countries. So let's take a look at an example. So imagine that you've been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while on the boat. What you need is a way to convert the length of the fish to its weight. So you contact the nearby Marine Research Laboratory and it provides reference data on the length in centimeters and weight in grams of the Atlantic Ocean rockfish of several sizes. Here's a scatter plot of that data. So what they said, they gave you all the data for the length and the width of a bunch of feet. And what you want to do is you want to create a model so a fisherman can just measure the length of the fish and estimate or predict its weight. Notice this is not a linear form. Oops. This is not linear. It is nonlinear. Well, wouldn't it be nice to make it a linear form? Well, we can. And the form that we are going to use is we're going to take length and we're going to cube that length. So these on my explanatory variable are x cubed. So they took the length of every fish and they cubed it. And that will help us accurately predict the weight. Notice this is now a linear model. Because the transformation made the association roughly linear, we used computer software to perform a linear regression analysis. So they made a scatter plot out of x cubed and y, and they got these values. So give the equation of the least squares regression line. Here's going to be my least predicted value of y equals a plus b x cubed, and define any variables that you use. And then I want you to suppose a contestant in the fishing tournament catches a rockfish that is 60 centimeters long. Predict that fish's weight. So pause the video and jump ahead. Alrighty, so if I asked you to make, given the equation of the least squares regression line, I said do this. So remember, A is my constant. A is the constant. B is the coefficient of x cubed, and it's labeled for me right there. So I am going to plug in those values, where y is my predicted weight, x is the length of my fish, because it said we got to define our variables. If you don't define your variables, you will lose points on your AP statistics exam. So define those variables. Plug in the value of A, plug in the value of B, and there is my equation. Boom. Now part B says take this equation and estimate the weight of a 36 centimeter fish. So I'm going to take out X and I'm going to plug in 36 centimeters. I'm going to go ahead and cube that 36 centimeters and plug all of that into my calculator, and I will estimate that this rockfish that is 36 centimeters long has a weight of 688.9 grams. Now you'll notice one of the things it gave us was r squared. So right here we had r squared. What does r squared mean? Hit pause, jot down what you think it means, and come back. So I'd like to remind you, r squared is the measure of the percent of the response variable that is explained by the value of the explanatory variable. So when r squared is 99.5%, that means 99.5% of the weight of the fish can be explained by the length of the fish. The rest of the 0.5 is something else. Did you say that? I know you did. We can also, instead of saying x cubed, what we can do is we can take the cube root of y. So we can work it around, and instead of saying y equals x cubed, we can say the cube root of y equals x. So that's what they did here. They said y is the cube root of 8. Same story. Y is the cube root of 8, where x is still the length of the fish in centimeters. Because our variables are slightly different now, we get a different table of data, but we can still write our equation, and we can still estimate the weight of a 36 centimeter fish. So go ahead and hit pause and do that. All right, so my equation, I wanted to do the cube root of y hat is a plus bx, where y is, again, going to be the predicted weight of the fish in grams, x is the length of the fish in centimeters, the actual length, and, did I not write, oh my goodness, I did not write down what the equation was going to be. So what my equation is going to be is the cube root of y equals, you know what, I wrote it down right here. Let's just jump ahead. There it is right there. There's my a. I didn't hide it from you. I hope you didn't cheat. Here's my a, my constant, right here. Here's the value of b, the coefficient of x, which is right here. Plug them in, and I get the cube root of y is 8.856. Cube both sides, and I get an estimated weight of 694.6 grams. Notice it's slightly different than the first time. That's okay, because we got a different table and all of that rounding and all of that good stuff. But the idea is still the same. We're really close. We're only like 6 grams off. So it's still a good prediction. All right, so what I'd like you to do now, never mind, I jumped the gun a little bit. So right here, I'd just like to say we can either do, these are the same way of doing it. We can do x to a power, y is a scatter plot, or x and the p root of y. Either way works. So on 3.3, go ahead, flip over to questions 1 through 4 in your assignment and answer those. And I'll see you when I get back on Wednesday.